In the past, if you still remember, we use Powe placement. Alright, Powe placement is to take the transfer function of a plant, if you still remember, and then you use the Diophantine closed loop Powe equation, ACL, and then you rearrange somewhat and eventually you'll find a transfer function for your controller. Alright, so for Powe placement, you somewhat use the transfer function of your plant to find the transfer function of your controller, if you still remember. In our case, we're gonna use Powe assignment. Alright, so it's not Powe placement. So be careful now, because now we're gonna use Powe assignment. So if you don't know anything about Powe placement, just go back to the previous few videos. Lesson 4, alright, introduction to Powe placement and so on and so forth. Okay, so therefore, what is Powe assignment? Powe assignment is that what happened that, if you still remember, this is the transfer function from our previous video. We have proved to you this. Alright, and then you're gonna shift, this is your open loop system. Your transfer function is an open loop. And you want to close loop such that when you close loop, you can have some values of your poles to have some other values. Instead of 7s, you have something else. Okay, so we want to shift the poles from s plus 4 times s plus 3, because if you were to spread this into this thing, you have, I think you get, you just expand only. Alright, so for Powe assignment, you want to shift your open loop poles at this s plus 4 and s plus 3 to some other poles such that it is like s plus 10 or s plus 20 in our example. Okay, so later on we will talk about how to shift your open loop poles to your closed loop poles. This is some zeros lah. Okay, so we only keen to look at the poles. Alright, so we want to look at the how do we shift the open loop poles to the closed loop poles. Okay, using these examples. Alright, whatever poles that you want depends on whatever poles that you want, because it can be s plus 200. You can also sub in as your this over here. It depends, all depends on you, which one you want to sub in. And in order to create a link between your open loop poles and your closed loop poles, you require a magic value of k. Not a value, but rather a matrix. Alright, if you still remember our a minus b, our ax minus bu, plus bu, sorry, this is your open loop system. So if you were to close loop, you introduce a minus k over here. You remember? So therefore, this minus k will contain information to tell you to shift the poles from s plus 4 times s plus 3 to s plus 10 times s plus 20, sorry. So therefore, let's start. And therefore, our objective is to have somewhat a poles that has s plus 10, s plus 20 as our closed loop poles. Okay, in order to have to reach this, one way is to create ACL, our closed loop poles. Alright, is equals to s plus 10, s plus 20. Alright, if you were to expand this thing, alright, what do we have? We will have s squared plus 20s plus 200. Okay, and in order to find k, alright, which is a matrix, alright, we're gonna use something with the same meaning as x1 and x2. If you remember from the previous video, or we're gonna continue with the state space. Alright, but so you know that we don't need to convert the old method of the state space, but rather when we can also use the canonical general form to represent our state space. Alright, taking note that this is minus an all the way to minus am minus infinity. Alright, so this is something that we have discussed earlier, because the initial state space general form has somewhat a little different meaning compared to this one. So if you happen that you want to remember this one, then the values of the placement of an, a2, or whatever corresponding to this is a little bit different. Alright, the previous video has discussed, you just watch. Focus here is only to determine what is the value of the matrix K. Alright, in order to do that, x squared plus 20s plus 200 is our objective. So we have a s squared plus 7s as our initial. So the difference between this thing, this pole, and this pole, what are the differences? The differences are simply 20s minus 7s is equals to 13s, for this coefficient of s. Because the differences for s squared is already the same, so there's no differences. The only differences is only 20s, 7s, which is 13s now, and then 200 minus 12. So I have 200 minus 12. What I have is 13. No, sorry, 118. All right. Sorry, 20. Is it 20? No, this is 30. Sorry, this should be 30. Okay, sorry, this should be 30. My fault. All right. So 30 minus 7 is 23. Okay. So the difference between your open loop poles and your closed loop poles is 23s and 188. Okay. 23s, as you remember, 23s is your x1, right? Because your x2 is simply equals to s to the power of 0. Alright, if you were to differentiate x2, you'll have x2 dot, which is equals to s to the power of 1. Alright, which is our s over here lah. Alright, so therefore if x2 dot is, so s2 dot is equals to x1, and we can just simply rewrite as 23x1, alright, plus 188. Alright, so 118x2, because x2 is simply s to the power of 0, which is equals to 1. Alright, so 118x2 to some extent lah. Alright, so we have 23 and 188. That's all. Okay, pretty straightforward, right? However, in our course of study, this thing may not be as easy. Alright, because this thing is easy for us, but they actually introduce something that is more difficult. Alright, they're gonna introduce the Ackermann system. Alright, where you're gonna do a lot of matrix multiplications, things like that. Eventually, you see, you take so many steps eventually to derive this one. Alright, but for here, you can just minus away and just get the value. That's it. We're only taking the n in mind, minus away the initial, you get this one. But for this case, the Ackermann one, you do all the way for a long chunk of stuff in order to get this. Alright, so therefore, I will not go into details on the Ackermann, but I just want to inform you that although this may sound easy, but this will not come out in your test. You just need to know only, that's all. Alright, but how does this k value, because in the end we will still need to find k value, because the Ackermann one also need to find the k value. Alright, because it's in terms of k, you need to find k. Alright, so how do we represent k? Okay, how do we represent k in terms of a canonical form? Okay, the canonical form for the closed loop is this thing, as you remember, a minus bk. Alright, where this is multiplied by x1, x2, etc. Okay, multiplied by x. So this thing is equals to your x dot, if you still remember. Alright, which is this one. I just simply rewrite as this whole chunk over here, and taking note that these are all n minus 1, n minus 1, all the way to n minus infinity. Alright, I'll not go into details of why, because there is a problem with this system. Alright, this notation system. In the previous video we have discussed. I just want to share with you that I bring this over here so that you can apply it easily. So what do I mean by this? Alright, so by right, the closed loop system, alright, x dot is equals to minus 30 minus 200, 1, 0. Alright, and x1 and x2. This is the form for a closed loop system, and your desired closed loop system, because this minus 30 and minus 200, if you find it familiar, is coming from here. Alright, and therefore, because you cannot straight away write in terms of this one, alright, although we can, but anyway, I will not go into details, because yeah, anyway, you know that this thing over here is equals to, can be re-represented into the state space of this one. Alright, this state space over here can be rewritten as this form over here, where your an, alright, is the first value of your system, alright, which is minus 7, if you still remember. Alright, so I'll just simply write as 7, alright, because an by right, it should be, if you remember, this is, where am I? This is an, okay, or this is a2 lah, then this is a1, okay, So this A2 corresponding to S, right? A2S, so A2S over here. Okay, so A2 is equals to 7. And why is it minus 7? It's because the canonical form changed it to minus, because minus AN. If your AN is a positive, like for example 5, then minus, you'll become minus 5. Or if your AN is a negative value minus 5, you have minus 5, it will become plus 5. Alright, so these are the things that you may need to consider and be take note of. Okay? The objective is that I want to pluck out the A2 value, which is 7. Alright, so I pluck out the value, I put it over here. So this over here is A2 now, and I'm going to use K2. Alright, my K2 over here is what? My K2 over here is, this is K2, this is K1. Alright, this is 23. Okay, and therefore plus 23. So 7 plus 23 is 30. 30, and then this outside is a minus, so minus 30. And therefore you can see you have your minus 30 over here. This thing is, if you take note, this is your canonical form, your matrix over here. So just simply sub it into a matrix also. As you can see now, I can re-represent the matrix. Likewise for this case, this is now AN minus 1. My N is 2, so therefore 2 minus 1 is A1. Maybe I should write as A1 plus K1. Alright, my A1 is what? My A1, as you know, is 12, right? Which is S to the power of 0, right? So my A1 is 12. So just simply write as 12 plus my K1 is what? My K1 is 188, right? I've shown you over here, right? What I have is 188. So 12 plus 188 is 200. And then 200, we have a minus over here, and therefore I have a minus 200, as you can see. Alright, well the rest are 1, 0. Alright, 1, 0. If you have 3 times 3, then you'll have the trend all coming out in this manner. Okay, I'm not going into details about that, but at least you get to see how the trend starts to come in. Alright, and then the closed loop system is somewhat represented by A and K. Okay, so if you add in mind, if you have your K and you know your A, which is where's my A? Okay, this is your A matrix, and you add them up together, you should get something like this. Alright, this is your closed loop. Okay, this is your closed loop. I repeat again, this is your closed loop. Alright, this is your open loop. Alright, and our purpose is only to find the K. And then after finding the K, we sub it into the closed loop system to represent our stuff. And the purpose of us doing everything, writing in terms of a state space, you still remember, is because your transfer function can be written into this form, right? This is for the open loop. For the closed loop, is this form. Okay, so if you want to re-represent your transfer function, then you can find your C, you can find your whatever S, your A, your B, and your K. You just rearrange your stuff, and you should have some values already. And you take note that your X0 is your initial value, alright, when you just started off, but it's just some constant value lah. Okay, but at least you get to see that after you get your A minus BK, alright, which is over here, you can just sub in over here, inverse it, and then you rearrange, and you get your transfer function. Alright, and therefore after you get your transfer function, then you can run your system already. Alright, so the whole process is this. Alright, you have your open loop transfer function. Alright, and then write it in terms of a state space by using the general canonical form of this one and the notations of this one and this one. Alright, once you write in terms of the state space already, okay, then you find your K value, and then your K value and your state space, your K value and your AN, which are all these constants over your A to A1, you just sub in over here to get your A minus BK. Alright, and once you get your A minus BK, you sub it in with you need to find your C ma. Alright, so therefore your C will be sub in over here, and then your SI. So I think you get what I mean already. So you just simply find, the purpose is simply to write in terms of a closed loop system, and that's all. Alright, this is the closed loop system. So you write your open loop system with certain poles over here, and then you rearrange, you find your K, and then going through all the processes of subbing and matrix multiplication, eventually you'll get back your closed loop transfer function. Okay, so we are changing from an open loop transfer function to a closed loop transfer function, where your closed transfer function has the poles that you want, s plus 10 and s plus 20 for our case, or for examples if you were to say. Alright, hope that this is pretty clear, and yeah. Alright, so in the next video, instead of going, because we know that there's an easy step, because we're just taking our closed loop poles minus away our closed loop open loop poles, you'll get your k already. But it's not as easy as we thought, because in tests you're gonna use Ackermann's. So therefore, in order to find k, alright, again we're gonna use the Ackermann's method, which is in the exams. Alright, so you're gonna use the Ackermann's method to solve with things. Alright, and therefore I'll see you in the next video for the Ackermann's method.